Hello, my name is Ben Morkos, and I'll be talking about implementing neural engineering framework-style networks on embedded FPGAs. This work is a collaboration between Applied Brain Research and the University of Waterloo. We've developed a Python-accessible PYNQ implementation that outperforms the Jetson TX1 GPU, computing neural engineering framework-style neural networks by 10 to 500 times while using 2 to 10 times less power. Our design is built for embedded applications, is designed entirely with high-level synthesis, and automatically tunes fixed-point precision. As we know, machine learning is a rapidly growing field. It's typically done in Python and is also very compute-heavy. And since Moore's law is ending, now we need some sort of custom efficient hardware to evaluate these models. And that's why we chose to go with the PYNQ FPGA. We target the neural engineering framework, and we use the Nengo Python package to do so. Now just keep in mind that the neural engineering framework has different structure than deep networks or convolutional networks, and we'll get to that in a few slides. So Nengo goes beyond deep networks and can accomplish things like dynamic models, real-time adaptive control, biologically plausible cognitive architectures, and hierarchical reinforcement learning. So this does cover a broad range of topics and is very interesting stuff. In fact, the world's largest functional brain model spawn is built using the neural engineering framework in Nengo, and that boasts 6.5 million neurons and can accomplish a range of different conceptual tasks. Nengo also has a graphical user interface, so here we're showing an example of a small learning network, and you can see the different groups or layers of neurons as well as their connectivity, and then the real-time represented values are shown in the plots. And just to give us a 10,000-foot view of the entire Nengo ecosystem, we have at the top rung some what we'll call optional add-ons. So we have that graphical user interface we just looked at. You can code directly in Jupyter notebooks. In fact, you can import models directly from TensorFlow. Beneath that, we have our core framework. So that's the main library in Python, and that'll take your high-level description of your model or your network and build some sort of network graph that can be evaluated. And then where we focused are these lower two rungs that take that network graph and map it to some physical hardware for evaluation, whether that be CPU, GPU, some custom neuromorphic chip, and with this work we're adding what we call NengoFPGA and map that network graph to the FPGA hardware. So now we'll compare and contrast the deep networks and the neural engineering framework style network. So starting with a deep network, typically we'll have some input at the top here, some output at the bottom, and some layers of hidden neurons in between. And then again with the neural engineering framework, we have some input at the top, some layers of neurons, and output at the bottom. You'll notice we just have this pinch in the middle, which is the main difference. So essentially what we're doing here is we're going to take that n by n weight matrix and factor it into two n by d matrices that we're going to call the encoders and the decoders, which just means between layers of neurons we're going to be going back out to a state space of representational dimension. And why would we do that? So since we have our number of neurons typically much greater than our representational dimensions, by doing this we save memory, since two n by d matrices are much smaller than one n by n matrix. We also save bandwidth, since we're now only transmitting that lower dimensional d vector as opposed to the large n vector. And then the neural engineering framework also adds a temporal dimension, which gives us the opportunity to sparsify through time as well as through space. Another interesting fact is that the encoders can be randomly generated, while the decoders can be pre-solved offline analytically or with typical methods like backpropagation, or they can be updated in real time with online learning. So now we'll take a look at more of the actual computation on the left side and try and map that to our high-level topology on the right. So this boils down to basically two matrix multiplies. We have our first one for encoding, where we take our input and our encode matrix and we multiply those together. And then we apply our neuron transfer function. In this case we're using the rectified linear units. And then we have our second matrix multiply, where we take that neural activity, multiply it by our decoder matrix to generate the output. And of course, if we want to have online learning, we add that feedback loop in there as well. So these are just matrix multiplies, and we know GPUs are great for matrix multiply, so why not just use the Jetson directly? In fact, the Jetson can do up to 1 teraflop of throughput. Well, in this case, we have relatively small networks, and we have no batching, so this makes it hard to keep the chip full. In addition, the GPU has limited on-chip memory to store all the weights, has no direct I/O access, and little flexibility in data types. So now we'll just take a look at some pseudocode and follow along. So if we have a single matrix multiply, that's fairly easy to parallelize and fill a chip. However, if we have 2 matrix multiplies with different structure, this becomes less obvious. And as you'll notice, we have our first multiply with a loop over n followed by d, and the second multiply with a loop over d followed by n. So, we'll address these challenges of parallelization despite having temporal dependency with the learning and no batching, and that structural difference we just highlighted, and then we'll talk about how we move to fixed point data types and use the chip resources more efficiently that way. Here we'll take some pseudocode on the left and follow along with the structure on the right hand side. And before we go any further, let's take a minute to estimate the required cycles this should take to evaluate. So we start with 2 loops over n and d, and then within each of those loops we have a load store operation on a floating point number. So to be conservative, we'll give ourselves 3 cycles for each of those. And then we have to do the neuron transfer function as well as add bias in, so we'll give ourselves 2 n cycles for that. And then of course, if we want that online learning loop, that's an additional load store operation inside the second matrix multiply loop, so we'll just bump that 2 up to a 3 inside the parentheses. So for example, if we have 200 neurons and 2 representational dimensions, this should take 4,000 cycles. However, our initial approach to directly implement this took 6,000 cycles. So now we'll look at what we did to mitigate this. The first thing we did was to restructure that second matrix multiply. So essentially we're just going to flip the loop bounds here, so now both of our matrix multiplies are loops over n followed by loops over d. Doing this improved our initiation interval and got us down to 4,800 cycles. However, if you take a look inside that second matrix multiply, you'll notice that our y vector iterates over the j dimension. So by flipping these loop bounds, we now have to store the entire y vector in memory instead of computing a single output at a time. So there is a bit of a trade-off there. So now we have our loop structures harmonized and we want to add parallelism. Unfortunately, simply adding unroll, data flow, and pipeline pragmas cannot automatically extract parallelism, so we had to put some manual effort into this. First, we add some explicit parallel structure, and we do this by adding an additional outer loop over some unroll factor ufac. However, by doing this, we actually generate partial results, so each parallel section is now generating a part of the output. So we had to add some additional logic to accumulate these into a single coherent output after the fact. And by doing this, we managed to get down to 400 cycles with an unroll factor of 12. So just to summarize, for our initial naive direct approach at 6,000 cycles, we restructured our loops, we added some explicit parallelism, and that gave us a 15 times improvement down to 400 cycles, while only using twice the resources. In fact, once we move to fixed point, we shrink our compute tile, and we can get an unroll factor of 28, and that further reduces us down to 90 cycles for an evaluation. So now let's look at how we move to fixed point. So we created 5 different fixed point types throughout the design using the Xilinx provided APFix template. For each of those types, there are 4 different parameters, and for each of those, multiple different possible values. So that leads us to about 10 to the 20 different configurations. So a brute force approach here is really not feasible, so we have to do something more clever. So we use a Python package called hyperop to automatically tune the hyperparameters and extract the Pareto optimal designs for a given cost function. Obviously, we want to minimize error and maximize performance, and how we did that was by directly minimizing the error and by minimizing resources. And the idea is if we can get a small high-performance tile, we should have more parallelism and overall improve the performance. So now we'll take a look at what HyperOpt is doing. So we have our description of HyperOpt in Python, and that'll generate some trial configuration. We'll pump that into our HLS design. We'll do a simulation, and that'll give us an idea of accuracy, and then we'll do our C synthesis to get an idea of cycles and resource. And notice here we're not doing a full place and route, so this is a relatively quick process. So now we can look at some results. So along the horizontal axis we have the maximum number of chip resources used, and along the vertical axis we have our absolute representational error. So we'll start with our floating point design over here on the right. So anything below that is going to be more accurate, and anything to the left is going to be using fewer resources. So anything in that lower left quadrant is a strictly better design. So now each of these blue points is one of the HyperOpt trials, and you'll notice there's quite a good number of candidate designs that are strictly better than its floating point counterpart. And from here we can also extract the Pareto optimal front. So for a given resource budget, we can decide the best accuracy achievable. So we let HyperOpt run for 3,000 trials. Here we have the trials along the horizontal axis and our normalized cost function along the vertical axis. And just note here, this is the best so far cost, so this will be monotonically decreasing. At this scale is not too much to look at, so now let's zoom in a little. So you'll notice here on the right hand side, after about 1,500 trials, we've converged to our best solution. And in fact, on the left side here, you'll notice that after just about 400 trials, we're at over 99% of the way to our best solution, and that only takes 4 hours on an i7 CPU. So this is a relatively quick and iterable process if you choose to change your design or change your cost function. So now let's look at some performance results. We evaluated our design on a PYNQ FPGA board, which uses a Zinc chip at 28 nanometer technology, and we compare that to a Jetson TX1 embedded GPU, which is in fact a technology node ahead at 20 nanometer technology. So here along the horizontal axis we have bins for the number of neurons in the model, and then within that we'll have the different colors of bars for the number of representational dimensions. And these two things together are what are going to dictate the problem size. And then on the vertical axis we have the speed multiplier, so the speed up of the FPGA over an optimized implementation on the GPU. So over this entire range summarized here, you'll notice there are some diminishing returns, but we are at least 10 times faster than the GPU across the board. And in fact, if we push out to the chip limits, if we go up to 32K neurons or 32 representational dimensions, the speed above the FPGA still falls within this range. So NengoFPGA is not only interesting as a research project, but we can accomplish useful work as well. So it's been shown that 3,000 neurons can form the basis of an adaptive motor controller, and using the FPGA over the GPU in this case would be on the order of 20 times faster. It's also been shown that 500 neurons can adapt and control a 15 joint body simulation, and in this case using the FPGA would be on the order of 50 times faster than the GPU. We also did a simulation where we control a variable mass inverted pendulum, and not only do we have comparable accuracy to the floating point design when using fixed point, but in this case the FPGA would be on the order of 200 times faster than the GPU. In summary, NengoFPGA is a user-friendly, efficient Python-accessible implementation designed for dynamic neural engineering framework-style networks that outperforms comparable devices such as the Jetson TX1. By restructuring our HLS code, we see a 15 times improvement in performance. By switching to our automatically tuned fixed point precision, we get an additional 4 times improvement for an overall improvement of 60 times compared to our initial attempt. And with that, we are 10 to 500 times faster than the Jetson TX1, while using 2 to 10 times less power, depending on the problem size. We continue to work on NengoFPGA to make it a seamless and fully featured backend of Nengo, including things like multiple neuron types beyond just rectified linear. We'd like to support larger networks with arbitrary and flexible connectivity, and we want better support for convolutional networks for those typical applications. NengoFPGA is available from Applied Brain Research, so to learn more or to purchase, head to our website at abr.rocks.